Thanks for coming. It's a pleasure to be here. So I visited about a year and a half ago, and then at that time I gave gave a talk on the work that we were doing at the time. So this talk is an update of the work, mostly the things that we've done since then. But for the benefit of those of you that might have been around, I know that this is a company that's hiring a lot of people. I'll just start with a brief review of the things, historical review of the things that we've done in the past. And then I'll go more in detail of the most recent ideas. Okay, so my work, or a significant part of the work that we do is in this area, a general area of image retrieval. And the basic idea is what's usually called content-based image retrieval. So we want to build systems that can search for images and learn to annotate images. We want to do that by analyzing the visual contents of the images. So the idea is to see what can be done without relying on metadata. There are, of course, many search engines already available that perform image search by the analysis of metadata, be it web pages or little timestamps that the cameras add to these images. But the focus of this area is more on trying to understand what can be done by looking at the images. So I'll start with by giving a brief description of the evolution of the field. This is a field that's relatively new, so it started around the late 90s or mid 90s. And the first paradigm that people came up with to try to solve this problem, it's what's called query by sketch. The basic idea being that you have some system, which I cannot see, that has a little canvas where users can basically sketch or introduce a sketch of the types of images that they're looking for. And so that was that slide that we had was about. It's kind of a limited interface because lots of times people don't really know how to sketch, or they don't want to, it's too much work to provide a sketch of what they're interested in. Right, and so towards the late 90s, there was a move. So this is like what I was talking about. There's a little canvas where you can sketch the things that you're interested in, but it's not very powerful. So towards the late 90s, there's a lot of work done on the area of query by example. And then since the turn of the century, there's been a lot of work on what's called semantic retrieval. So let me briefly go over these two in a little bit more detail. So a query by example system is a system that supports similarity or image search by strict visual matching. The basic idea is shown here. The user provides the retrieval system with some example image. The system extracts a collection of visual features. It could be about texture, color, shape, or whatever visual features might be deemed relevant. Then that makes a little signature, which is extracted from the query image. It's compared against the signatures of all the images that are in the database, and the top matches are returned. And so, like I said, during the 90s, there was a lot of work in this domain. And you can ask questions such as, what is the optimal retrieval system under this framework? And in fact, we've done a lot of work where we try to come up with, a framework for doing this operations in sort of an optimal form. Most of our work ended up in this area of minimum probability of error retrieval. And this is where we formulate this matching operation as a classification operation, and then we can ask what is the optimal decision function for image ranking in order to minimize the probability of the matching error. Of course, a retrieval system is not only about image similarity, so that's only one of the part of a retrieval system, there's a whole other sets of things that needs to be done. And ideally, this formulation should be such that it also is helpful in the solution of those questions. So questions like relevance feedback, indexing, how do we design this classifiers so that they're scalable and they can be applied to large databases and so forth. And this minimum probability of error formulation turned out to be a nice, global solution for all these questions. And one of the lessons that we learned is that when one is trying to solve all these problems, one cannot really rely on, very complicated matching functions. And so all the retrieval systems in this area turn out to rely on image similarity operations that were, relatively simple. So here's a depiction of the core of our system. So basically, we have images. Images are decomposed into bags of local features or local feature vectors. There's a huge literature on machine vision with respect to local features or local descriptors for images, and pretty much any of those can be used. And then we basically formulate the problem as one of statistical classification. So we estimate the density associated with each of these images. So we fit a Gaussian mixture to the cloud of points that's extracted from the image. And then we look at these models as different classes that are available in the database. And the similarity function or the decision function is just a Bayesian decision rule. So whenever we get a new query, we do this feature decomposition, and we compute the posterior probability of the query under all these models, and that gives us a ranking for the images in the database. So this is the basic retrieval query by visual example type of operation. At around 2000, this was the state of the art, or systems like these were the state of the art in the field. So here's an example evaluation in terms of precision recall, but the details of these are not that important. What's important is that with a system like this, it is possible to make image retrieval work. But only for certain types of queries. And those are the queries where similarity literally means visual similarity. So let me give you some examples of this. Here we have some results, queries. Once again, this query by visual example paradigm. These are like 4 queries. Each row presents the top matches to each of the queries in the database. The database is about 2,000 images. They're very diverse, as you can see, throughout these queries. Once again, so the results are good when there's like a strong degree of strict visual similarity between the query image and the images in the database. And notice that the system is kind of relatively good at finding what are the dimensions of this feature space along which similarity is strong. So in this case, it's mostly the fact that these images have similar colors. For this one, you see that the colors are actually different, but it locks on the fact that all these flowers have kind of petals that have the same sort of shape, and so forth. So the basic idea is that this can actually work fairly well if there's a direct match between the query image, the appearance of the query image, and the appearance of the images that one is trying to find. However, in practice, visual similarity does not always correlate well with semantic similarity. So here's an example of a query where the system fails. So this is an example of a queried image that has airplanes on an airfield. And these are the top 4 matches that result from this query by visual example operation. And if you look at these images, in terms of strict visual similarity, they're actually reasonable matches. So all these images have some amount of sky in the back, like the query, they have a sort of like geometric structure that looks like a plane under perspective. In the foreground, once again, like the query image. But the fact is that for people, these don't really look like very similar to that image. And in fact, they look a lot similar than these images here. And notice that what makes these images similar to that one is not the fact that they have sky or there's a ground plane, but as the fact that there's these little things here called airplanes that we say, okay, this is an image that has airplanes. These are images that have airplanes. And that happens even though these airplanes are just a little fraction of the image. They don't really look like much like those ones. These ones are yellow, those ones are white. The wings are different, they have different shapes. Here there are 3, over there we only have 1. It's a very different type of similarity, which is not correlated necessarily with the fact that the images look the same from a strict visual standpoint. And so that led to this idea of semantic retrieval, into which the field has evolved. And the basic idea is that first you learn to annotate the images. So given an image like this, you would annotate it with a keyword such as, this image contains airplanes on a hair field. And then you would do the match directly at the annotation level. So you would look for other images that contains airplanes on airfields. And that's the basic formulation. So we want to search, images are compositions of semantic visual concepts, and we want to search for similarities in terms of those visual concepts. The starting point for a semantic image retrieval system is some image database which is annotated with captions that are drawn from some finite vocabulary. And where each of these captions consists of a number of keywords, and each keyword corresponds to a visual concept. Typically you would have an image like this, and a caption that says something like people, beach, sand, palm trees, huts, and vacation. Now this is not a very standard machine learning problem in the sense that this labeling is pretty weak. So it's still a supervised learning problem in the sense that, for each image we get a caption, but we're never explicitly told what is the correspondence between captions and captions and pixels in the image. So I know that there's people in this image, but I don't really know that these are the people pixels. I only know that there are some pixels somewhere in there that are related to this concept of people. And furthermore, the captions are not necessarily exhaustive. It's fairly hard to come up with to predict what are all the words that could possibly be relevant to label a given image. For example, here, one could say that this image contains bathing suits or something like that. But somehow the person that was annotating or labeling the image didn't think that was relevant. The point is that we have to be able to kind of deal with that, the amount of noise. The goals, the main goal is to learn the mapping between these visual features and keywords. And we want to do that in order to be able to solve 2 problems. The first one is what's called semantic annotation. So if I know this mapping between words and features, well, given a new image, I can extract features from it, and then I can find the best caption for that image. So I'd like the system, when given an image like this, to say something like people, beach, sand, boats, trees, and rainbow, or something like that. And then the second problem is that of semantic retrieval. Okay, well, given that we know how to annotate all these images, then we can support retrieval by just matching these keywords. If I want to collect, look at a bunch of images like this, I can just say, show me images that have people on a beach, and then hopefully the system will be able to recognize, to find the images that contain those visual concepts. Now, from a mathematical point of view, Both of these problems can be formulated as problems in statistical decision theory. We have some data representation. In this case, images are just collections of feature vectors sampled from some stochastic process X. And the keywords are just, and the captions are just collections of labels sampled from a random variable W that's defined on our vocabulary. And we also know what are, the optimal decision functions in this minimum probability of error sense, both for annotation and retrieval. If we want to annotate an image, so we're given basically a bag of feature vectors extracted for the image, and all we have to do is to find the concept that has the largest posterior probability given those features. On the other hand, if we're given a concept on a retrieval operation, we want to find what is the image that best satisfies the query for that concept. Well, all we have to find is the bag of feature vectors or image, which has the highest posterior probability given the concept. So mathematically, this is not very different from the visual similarity type of problems that we were looking at before. But the problems, of course, is in learning this relationship between words and visual features. So we need to estimate these conditional probabilities from W to X. And that's problematically, in particular, because we do not have clean training data, so it would be relatively easy. I mean, nothing is ever really easy in computer vision. It would be relatively easy if you had a training set where, like, all the, for example, if you're doing face detection, usually you get a training set that consists only of very nicely cropped pictures of faces. But here, our annotations are only causal. So once again, I know that this image is of people, and it contains some feature vectors that are related to people, but it also contains a lot of feature vectors that are unrelated. So in essence, this is a problem of learning with lots and lots of noise. So basically, it's a problem where even our positive examples are kind of quite noisy. Some people have looked at this in machine learning, and the framework that has been advanced to deal with these sorts of problems is what's called multiple instance learning. The best way of thinking about multiple instance learning, to me, is through an example. So we can think of each image as a box of chips, like you would have in a casino. So each of these little feature vectors, you can think of it as a chip that's drawn from a certain concept. And concepts are really just cells on this probability, on this feature space in which these feature vectors are defined. So basically, a concept defines some region in the feature space, and then these feature vectors are sampled from that cell. So let's assume, for example, that all we're trying to do is to learn about image colors. So an extremely simplistic problem. So the concepts are image colors. And the chips are the image pixels. So here we don't have any features to simplify the matter, but only that we're only really trying to look, learn pixel colors like green or red or so forth. Now, in this case, the concepts are just, the cells associated with certain colors in color space. So, the cell of green colors, the cell of red colors, and so forth. And let's consider, for simplicity, that each image only has two colors. So here, this image has a lot of pixels that are red, so it has a big stack of red chips, and it has a smaller stack of green chips. And suppose that we want to learn, what is the probability distribution for green from this representation. Obviously, from one image, it's very hard because most of the stuff is not actually that color. There's a lot of stuff that is relevant. This big stack of red chips. But the idea behind multiple instance learning is that if we collect a large number of images and the background stuff, in this case the red background, is actually random, meaning that in different images it's sampled from different processes. So by assembling a very large collection of images, we can actually estimate the probability mass for the concept of interest. And you can see that. So if we have a collection of images where these little squares are always green, and then there's like a background that is drawn from some other color, even though in each image we only have a little stack of green chips, as we put together this big ensemble of chips, the green pile is at some point going to dominate, and the background, on the background we're going to have basically a uniform distribution over all the other colors. And so that's the basic idea. The basic idea is now for visual concepts, if we have a large collection of images that have a certain visual concept and then randomly drawn backgrounds, then if we collect a big set of images, a large set of images from that particular concept, and we fit a probability density estimate or a probability model to the whole ensemble of images, then at some point it will converge to the probability distribution of the concept of interest, plus some background distribution, which, because it's uniformly spread throughout the space, typically has a small amplitude, and it becomes the probability of the concept of interest becomes dominant. So that's quite interesting, and it's interesting in part because it's very compatible with the sorts of things that we were doing before for visual matching. So it turns out that if this holds, then all that we have to do, for example, to learn probability distribution for the concept of a mountain, well, is to get together a large collection of images that contain mountains on them, and then compute our features, dump all the features into a big training set, and fit a probability distribution to this concept of mountain. And so since we already were computing individual mixture models for the different images, it turns out that this can be done very efficiently. So there are methods for hierarchically estimating the density of all over the entire grouping from the individual densities. So we don't even have to go back to the feature vectors that extracted from the images. And so this process is so efficient that, in fact, this is what we were doing before for image indexing. Basically, given these images, we're just grouping them randomly, and we're creating sort of a tree structure of probability densities that then we could search very efficiently. All that we have to change here is to change this grouping so that they're, satisfy these labels. They are compliant with these labels that are associated with these images. And so once again, this is kind of a simple method, but it turns out to actually work, fairly well, and in fact, better than like all of the things that have been proposed in this literature so far. Over the past 2 years, we've actually done a very extensive evaluation of this, which will come out in a PAMI paper soon. Across multiple sets. So one of the sets that's commonly used in this literature is a set of images from Corel, which has been annotated. So there's about 5,000 images. They have been annotated with a total of 374 concepts. Each image has 1 to 5 labels. Here is a plot of some of the measures that we use. So there's, of course, multiple measures that are used, both for image annotation and for image retrieval. I'll not go in detail over all the, experimental evaluation here, but I just wanted to give you a sense for the evolution that has been happening in this area over the last, 5 years or so. So these are, here is a performance. So these are annotation results. There's 260 words in the test set. And this is a plot of the number of words that have recall greater than 0. And that means that the word appears as one of the top 5 labels given to the image. And so, you can see the earlier systems, the performance was pretty bad. Today, we have more acceptable results. So, like I said, out of the 260 words, we can do about 137, which is, of course, not perfect. But, there's certainly progress going on in this area, as the plot shows. And 5,000 images is kind of small. There's also a data set that has 60,000 images that was put together at Penn State by James Wang. This one is actually even more challenging. It has 442 concepts. The images are annotated in a noisy way, meaning that the fact that an image is annotated with a label does not necessarily mean that it has that label. And it turns out that as long as that noise is not that bad, so you don't have more than 1 out of 5 noisy labels, then the performance does not change that much. So these systems are relatively robust to this sort of thing. Okay, but so we certainly made some progress in semantic retrieval. In some sense, this is like the stuff that I talked about last year. So I want to do a lot on this again. Ever since then, we've been trying to think a little bit about what are the implications of this for image retrieval, and in particular the question of did we make any progress? Do we have any benefits of moving from a query by visual example system to one of these semantic image retrieval systems? And one can say, yeah, semantic retrieval is a lot better because we are now dealing with concepts and people want concepts. But the truth is that there are advantages and disadvantages. The largest advantage of semantic retrieval is that it works at a higher level of abstraction. For example, because if I want to learn the concept sky, because the semantic image retrieval system learns from a collection of sky images, it can learn the fact that sky is sometimes blue and sometimes is orange. If you have matching strictly by visual similarity and you give a system an image like this, the system has very little with which to work with, and it's very hard for the system to realize that, oh yes, this is sky, and by the way, some sky is also sometimes blue, and make that sort of generalization. So there's certainly an advantage for semantic retrieval in terms of working at this higher level of abstraction. On the other hand, there are problems like multiple semantic interpretations. Whenever we try to label images, it's kind of a tricky business. If you show an image like this to a number of people, to like 5 people, you're probably going to get 5 answers. Some will say it's a people of a lake. Others might say it's a picture of a boat with some people in it. Others might say it's a picture of fishing. And others might just say it's a picture of people on vacation having fun or whatever. So it certainly increases the complexity of the problem. And there's also the issue of the limited vocabulary. Okay, what if I want to find images of fishing, but the system does not know about that keyword? What do I do? Query by visual example is unrestricted by vocabulary. It doesn't have any. So if I want to find images of fishing, I can just provide the system with an image of some people fishing. And if there are other images that have boats and people standing on them and large masses of ocean, it's probably going to find those images fairly well. And so it generalizes better in that sense. And also, of course, there's no problem with these multiple interpretations because it does not really try to interpret the images. On the other hand, we've already seen that visual similarity is kind of weakly correlated with the notions that people have when they evaluate similarity, and so that's problematic. So that got us thinking into, can we somehow draw from the visual matching experience in order to try to improve the performance of this semantic retrieval systems. And the main problem, if you think about all these problems of semantic retrieval, are due to the fact that we specify queries in this very limited form where we just want to type, give me an image that has water. Well, that's the same as specifying a vector of probabilities for all these concepts that the system knows about, where water gets probability 1, and then everything else gets probability 0. And that ignores this rich description that internally the system has for the images. And in fact, that is the sort of the problems. For example, an image like this, it's probably labeled with the system, by the system as having some probability of being about water. Some probability of being about a lake, about people, about boating, and so forth. And so because all these probabilities have to add up to 1, all these possible competing explanations kind of reduce the probability of water, and so that makes the image a poor match to that query, which does not seem to make any sense. And also, by specifying queries in this way, we're basically just restricted to the words that the system knows about. Or, of course, you can use text processing tricks and kind of try to expand a little bit. But at the end of the day, you're kind of always specifying the question as the presence or absence of some concepts. And problems like, out of vocabulary generalization and things like that are difficult to deal with. It seems that the problem is that the system is ignoring this rich description of each image that the system contains. And so it's interesting to look at some of these probabilistic vectors, or these vectors of probability vectors of probabilities which the system annotates image. So this is what's shown in this slide for an example image. So basically, each image, we extract the features from it, and then we compute the posterior probabilities under each of our models, things like sky, mountains, clouds, and so forth. And then this is basically a multinomial distribution, and so we refer to these as semantic multinomials for short. And so here's the semantic multinomial associated with this image. And as you can see, for example, for this image, it kind of assigns, it doesn't really say specifically what image this is, what type of image this is, but it assigns some probability of even having trees and having houses and gardens, and then some other things that might not even make sense, like mountains or grass, which in this case is okay. But typically, you get some probabilities which make sense and which tend to dominate, and then you get a distribution of probabilities over the concepts that the system knows about. Sometimes those probabilities are just noise, like mountain here, which is unrelated to this. But sometimes they convey important information because, if you have houses, then many times you have grass nearby, and that might be like a good clue with which to match our pictures. Very briefly, another example. So this is here just for mountain and park. As you can see, sometimes it makes errors like it thinks that there's this big blue patch here is due to that it labels the image with some probability of being about oceans. So these probabilities are certainly noisy. It's not like we can ever, we will ever be able to come up with a perfect labeling system that can, give us a probability distribution which makes absolute sense. But altogether, there's a significant amount of information which is useful, and just trying to restrict that to a single label or a couple of labels, it's usually not a good idea. So this is just an alternative, form of retrieval. Once again, a simple idea, which is what we call query by semantic example. And here, instead of words, as is usually done in the retrieval paradigm, we go back to having the user provide an example image. That image is then labeled with this semantic multinomial, so with the posterior probabilities of all the concepts that the system knows about. And then these semantic multinomials are then matched. This semantic multinomial is then matched to the ones that were previously extracted from the database. And so if you're an information retrieval guy, this is similar to query expansion, but it's kind of a funny sort of type of query expansion where we're basically using an image, and then the image gets expanded as a vector of probability along all the semantic concepts that the system knows about. So what are the advantages of doing this? Well, as an extension of standard retrieval, now instead of just giving a couple of keywords, we give a specification as a complete probability distribution over the set of concepts that the system knows about. And this basically eliminates the two main problems that we were facing. First of all, if this image has multiple interpretations, well, the system will assign those multiple interpretations to it. Internally, it will represent this image with some probability of being lake, water, people, sky, boats, and whatever. So we're not really nailing down what the query is. We're kind of just giving the system an example, and then we're letting the system figure out in its own internal representation what are the possible interpretations that this image has. And also, it allows us to deal with the semantic space, outside of the semantic space issues or out of vocabulary words. So I'm no longer saying that I want an image of fishing. I'm just showing the system an image of fishing, and I'm letting, once again, the system translate that to whatever internal description it has. And so because of that, we have much better ability to deal with these two problems. When compared to the query by visual example that we were doing initially, well, it's the same paradigm, so it has all the advantages of query by example. But on the other hand, we're now dealing with a semantic feature space. So it's like we were doing the matching operation, but now at a space that has a higher level of abstraction. And for example, sky can be both blue and orange. And so that has typically better generalization. So it's actually interesting to look at this semantic space. So basically what we're doing is the space is the simplex of posterior complex probabilities. And each image is basically represented as a point on this simplex. And because we know how to measure distances on probability simplexes, even operations like measuring similarity and so forth are kind of trivial, and there's many well-known solutions for this. So we tend to use the callback level divergence as our measure of similarity in the simplex, but whatever other measure of distance between probability distributions could be used as well. Okay, so the main question then is generalization. So how do these systems generalize? How are they able to deal with these types of problems that I've mentioned? And there are two types of generalization problems, or there are two types of classes of queries. On one hand, we have what we call queries that are inside of the semantic space. And the other hand, we have queries that are outside of the semantic space. So what are these? So if I have a system that has been trained to know about mountains, cars, and so forth, if the query image is an image that contains mountains, then that's basically inside the semantic space. The concepts of interest are concepts that the system knows. If the image is an image of fishing, and I never trained the system to recognize fishing images, then it's outside of the semantic space. And so in terms of the generalization, we already saw that query by visual example doesn't care about this. It has no notion of spaces. Semantic retrieval only works inside this semantic space. And the question is, how well does this query by semantic example do, both inside and outside? And so that's something that we've been looking at over the past 6 months. And here are some results in terms of performance. So let me show you first performance inside of the semantic space. So once again, we're using this set, the Corel 50 set. So there's, of course, a training set and a test set. The images from both are images of the same concepts. And so for that reason, we say that this is inside of the semantic space. So the queries are inside of the semantic space. Here's the curve of the precision recall for the system. As you can see, so in blue, we have the performance of query by semantic example. In green, the performance of query by visual example. As you can see, there's a significant improvement of precision at all levels of recall. So this was more or less expected, and this just reflects the fact that this semantic representation has higher level abstraction. The fact that it knows that sky can be blue or orange. So that was expected. More interesting is the performance outside of the semantic space. And here we're once again training the system on this Corel 50 set. But both the retrieval database, the database that's searched, and the query database, the database of queries, are images that have concepts which are not in this training set. We've obtained these data sets in one case by downloading images from Flickr, and in another case by looking up some further classes of Corel which were not used to train the original system. And so here's the performance of the first experiments that we did in this area. And the results were a little bit disappointing. So as you can see here, the performance does not change that much from one training set to the other. But basically, the conclusion is that outside of the semantic space, there's no advantage for using the semantic representations. And so this is kind of not very exciting because, okay, we know that there's some advantage. We've seen that there's some advantage inside of the space, but most of the queries are probably going to be outside of the space anyway. So this was a bit problematic. So that led us to look more closely at these labelings that the system produces. And here is a typical example from a class outside of the space. So this is a class of commercial construction that the system does not know about. It's fairly typical in terms of what happens. So what happens is that these probability estimates are noisy, like I said. If you look across the set of these images, the correct labels or the best labels for these images, they kind of consistently appear among the top 10 or 15 labels for each image. So in this case, you have things like people, buildings, streets, and even tables. It's kind of these guys tend to be sitting on things that look like tables, so it's kind of a decent label for this image. However, when you look at each image individually, there's the correct labels do not always appear at the top. And if you look at any particular image, there's the probability of a random label just creeping in is not irrelevant. So you get things like water, boats, tree, restaurants, sky, and things like that that creep in, but those creep in more or less randomly. Okay, and so one can think of this, again, as a problem of multiple instance learning. So what we have now is a collection of semantic multinomial distributions where part of the distribution, part of the probability is the probability of the concept of interest in this little diagram, the green and blue bars. But then there's a bunch of probabilities that just appear and are basically just appear randomly. And so, from this principle of multiple instance learning, it should be the case that if we collected a large number of these and we computed the overall probability over the whole ensemble, this thing should converge, once again, to the probability distribution of the concepts of interest plus, some uniform distribution that's just roughly equal for all other concepts. Now, it turns out that for multinomials, this sort of operation is extremely simple to do. All you have to do is average them. So it's literally just like a noise cleaning type of operation. You just have to compute the mean semantic multinomial. And so, for example, in this image construction example, if you do this for all the 4 or 5 images that I showed you, you see that like people becomes like very predominant as the main label for this image. Then there's buildings, street. There's kind of this bogus label, which is statue. Then tables, and then there's a bunch of other things that appear that have much smaller probability. So there's a total of 371 concepts. So, this is really just the top 10 annotations.
Why does it have a restaurant there?
Well, that's another interesting. Okay, so the question is, why is there a restaurant there? And that's another. Let's save that question for the end, because that's something that I want to talk about actually, because it has to do with the fact that this a lot of time does contextual sort of associations. So here for this image, if you look at the label table, it's actually not that bad of a label, because these people are standing on, they may not be called tables, but they look like tables. What the system has learned is that when you have an image that has a lot of tables, then there's this, a significant probability that it's about restaurants as well. Okay, and sometimes that can actually be very beneficial, and sometimes that's actually what allows us to do these operations. But I'll talk a little bit more about that at the end. Okay, so the basic idea then is because this is easy to do, it's just averaging these semantic multinomials. Let's just, instead of using one single image, let's use a query composed of multiple images. So we collect these images, we compute their semantic multinomials, we compute the query semantic multinomial, which is just the average of this, and then we use that to search the local database. Okay, and so it turns out that when we do this, we have a very significant gain. So here are numbers of the mean average precision as a function of the number of query images. And once again, so here in blue is query by semantic example, and in red is query by visual example. You can also do query averaging for images and visual matching. So it's you can try it in that domain as well. It turns out that, as you can see for this semantic representation, there's an increase up to about 7 or 8 images, and then the performance is more or less stable. While for visual example, we don't really see any improvement. In fact, the performance tends to decrease as one increases the number of examples. If you look in more detail, one can see that this improvement happens at all levels of precision, or the improvement in precision happens at all levels of recall. And typically 2 or 3 images in the query are enough to make up most of the gain. And furthermore, these observations are quite consistent across data sets. So here are results. So here are plots of precision recall inside of the semantic space and on the 2 data sets outside of the semantic space. And as you can see, so the comparison to query by visual example is shown here in green, query by semantic example in blue, and the gain is significant. These are tables of mean average precision, and you can see that the increase goes from 30% to 100%, meaning that the mean average precision actually doubles. Yeah, so this, we did like the best performance that we could get, I think it was like up to 5 images. So this is the best precision recall curve in both cases, using up to 5 images. No, the single example, single example is this. Okay, you don't get any, there's no difference between inside and outside of this. Outside of the semantic space, you don't get any advantage. Okay, so this is like just mean average precision, and this is the same, but it's showing a precision recall curve for the, the top performance. No, this is inside, so this is inside here, and this is outside. Okay, so the question was if these plots are, there's kind of if these plots are inside or outside of the space. This one? This one I'm actually not sure. I think it's probably outside, but I'm not sure. I have to look it up. But you know, the basic idea is that it doesn't make, we don't see any changes, any differences. That's the, you know, one of the most interesting conclusions. As you can see, I mean, these plots are pretty similar, you know, across data sets. This is Flickr, this is Corel inside of the semantic space, and they're very similar. Okay, so you can ask the question, is it really the semantic structure that's you know, leading to this improvement? And one of the nice properties of this framework is that it allows us to explicitly ask that question, because remember, at the end of the day, we're just using this probability distributions. The representation for query by visual example and query by semantic example is basically the same. And we can test, what if we completely mess up the semantic structure by estimating these so-called semantic models from groups of random images. Okay, so let's disrupt the semantic structure. And what you see is that, so that's shown in red here, the performance drops quite significantly, and it's inferior to the performance of query by visual example. So there's certainly a gain there, which is significant due to the fact that we're doing this representation at the semantic level. Okay, so that's you know, the bulk of the message. There's this question left, which okay, there's this question left, which is how do we get these query images? And that's always a question for query by example. And we're just starting to work with this. But see, because now the examples are semantic examples, we should be able to kind of be, you know, find good examples by just using a regular search engine like Google search. So here's you know, the system that we're building. So there's, you know, we use Google search to kind of find a collection of images. So suppose you want to find pictures of your, you know, a wedding that you have attended, you know, next to the Eiffel Tower or whatever. We use the Google search engine to find pictures that have the Eiffel Tower on them. Then there's some intermediate stage that kind of gets rid of cartoons and things like that, graphics and things like that. And then we use these images to query our local database. Okay, so from the point of view of the user, this is once again just semantic retrieval. So the user doesn't really have to, you know, worry that much about gathering examples, which is always a hard task, because basically the search engine is kind of translating this textual query into a collection of images that then we can use to search our system using this query by semantic example paradigm. And so we're, you know, this is very recent thing. My student put together last week. But we're literally like starting to build this. These are some images that if you go to the Google webpage, they might still be the top matches for nesting birds. And so we fed those images to our search engine and you know, our internal database, and that's the stuff that comes out. So this is the basic idea of, you know, using like Google as a translation engine between like the high level representation at which people like to work, which is, you know, text or textual queries, and you know, a local database which is not annotated, you know, at least not manually annotated. But so the basic idea is, you know, using query images themselves as queries to search the local database. Okay, so somehow it looks like I lost my thing there. So I just wanted to finish anyway with the conclusions. You know, the basic idea I think is that there's been some interesting developments in this area of image search. We certainly have not solved the problem yet, but I think that this kind of gives an idea of the progress that has been happening. I started by talking about this progression from, you know, sketch-based interfaces, which are not that useful, to then, you know, visual examples, semantics, and now we're proposing this notion of semantic examples. Query by semantic example, you know, I think it's can be pretty powerful when combined with this idea of multiple instance learning. One theme that has, emerged, I haven't really talked about that much during the talk, but as we've consistently seen in our work, is that typically the simple models, using simple models learned from lots of data and careful parameter tuning and things like that, tend to work a lot better than very complicated probabilistic graphical models and things like that. So we've all of our work, as you can see, is based on a very simple representation. There's this mixture models of local features, and every time we try something more complicated, the performance actually drops. So that's kind of an interesting observation, I guess. And I think there's, one can make a case that there's an intrinsic advantage for using semantic representations. As you can see, this is a direct comparison. The visual representation is exactly the same. It's just these mixture models of local features. And the only difference between that can explain the performance of these systems is the fact that we have these semantic groupings. So it certainly seems to be like an interesting area to explore further. And in my view, I mean, in terms of a bigger sort of philosophical point, I think it also points out for a different way of thinking of computer vision than what's typically done. So basically here, we don't really have very good classifiers. We have lots and lots of reasonable classifiers. And then certainly by moving on to the analysis in this higher level semantic space, we're certainly seeing improvements over whatever we have tried along the lines of using better models to represent the visual appearance of the images. And so it's certainly something to think about. Most of the emphasis on vision is towards building better models for appearance and invariance and so forth. And these results, our representation is quite simple by the standards of what's being tried today in the literature. And like I said, we haven't seen big improvements in trying more complicated things.